Thanks for joining us again, and hope you had a very good session yesterday. It was very interesting to listen to the kind of new ideas that Professor Anil Gupta put forward, of where he said the onus is on the teachers also to kind of help children be curious. You don't have to. There's no mantra for making somebody curious. They're born curious. Okay. This today we continue these topics, but we get into specifics. Professor, very happy to have Professor Narayanan Srinivasan. He is at present at IIT Kanpur. He was previously also, he's still associated with University of Allahabad, CBCS, that is the Center for Behavior and Cognitive Sciences. His undergraduate degree is in physics from the University of Madras. He obtained a master's degree in electrical engineering from IISc and specializing in biosignal processing. And then he went on to do his PhD in University of Georgia and then moved to Allahabad in 2003. Okay. He has a long years of experience, expertise in this area. His initial investigations were in interaction between attention and spatial frequency processing, which is, attention is a very important topic. It's actually a one core topic when we talk about learning and education. His research has wide spans. For example, he's even done research on meditation, but language and meditation. Again, language is very important when we talk about bilingual, multilingual that we see in India. And he's currently working on a project which is interesting, which is on looking at neural basis for cognitive reserve, role of bilingualism in education. So that's also something that if you have questions on language, you can also ask him maybe during this talk, if his talk covers it, or maybe afterwards. He's a fellow of National Academy of Psychology in India and and fellow of Association for Psychological Sciences. He's an associate editor in many journals, one of them being Frontiers in Cognitive Science. He's published numerous papers, and I think there are a lot more that I can actually talk about in terms of his introduction, but his webpage is linked to the profile that we have given on the website. Please go to have a look. Look at the number of papers, the kind of papers that he has written, and the relevance it has to education. So without much time, I thank Professor Srinivasan for taking the time. Very important. And thank you, sir, for joining us today. Over to you, sir.
Sure. Kavita, thanks a lot for inviting me and giving this opportunity to talk to both learners and teachers. Let me share my screen. Okay. Kavita, can you see the PowerPoint?
Yes, sir. We can see it.
Okay, so a couple of kind of disclaimers. Number one, I'm really not going to talk too much about my own work. Some of it has some relevance for education, but not really directed towards education. So I thought I will make the talk a bit more general. But I do think cognitive science is very important for education and instruction. And what I would like to convince you, if you are not already convinced by the end of the talk, is to take cognitive science seriously and then use it to educate the children or adults as well. So what basically this talk is going, I will give a brief introduction to what is cognitive science. Some of you may well be familiar with it, but some of you may not be familiar with the language that people use in cognitive science. So I will kind of give a brief introduction to cognitive science. I will talk about some cognitive processes, attention, memory, problem solving. Then I will talk about some work. It's actually slightly older work because that's what I'm more familiar with. related to cognition and education. And, and we will conclude. So, this is taken from a book by Rife. Normally, we think of input, something we say teach or a stimulus we give, and then we measure performance. All of us do that. And the next step is to say that now there is this black box, but inside the black box we have knowledge, which is stored, memory, and we have various thought processes that essentially combine information or concepts and then to arrive at other things. So what cognitive science says is if you have a complex system like the mind, it can be understood in terms of description at 3 different levels. This is essentially what we call the computational view of mind. This is based on David Marr's work. And the basic idea is you can look at the system at 3 different levels. The first level is computation, exactly what kinds of things minds compute. What are the capabilities of the system? What is computed? The second level, which is really even more important for the talk today, is the so-called algorithmic level or the representational level. Essentially, the questions here are, given that something is being computed, what kind of algorithms that we use, what kind of symbols or representations that we use, how we take these representations and then transform them into other representations. And of course, one can also talk about the brain, how these things are implemented in the brain, and essentially see how neuroscience is linked to cognition. I will hardly really not talk too much about the brain. There is a lot of important findings and implications for neuroscience as far as education is concerned. Let's just take a simple example to make this point so that those who are not familiar with this, it's clear that, what we are talking about. Let us take something as simple as multiplication. And essentially what we do in multiplication, we take 2 numbers, x and y, and then we multiply them and we get some answer. This is the computation, a calculation that we do. The algorithm is how given x and y, you calculate the output, z. And there are many ways to do this. Of course, one example is shown here, which is essentially a table, a lookup table. And you can go and see, okay, the 2 numbers are given in the row and column, and then I will find, track where the answer is. So 3 is here, 5 is here, and they meet at 15. So 15 is the answer. Now, this is a way of doing it, and there are many ways to do this. You can also do repeated addition, for example. If I am interested in 5 into 3, I can say 5 plus 5 plus 5 3 times and come up with the answer 15. So there are different algorithms to perform the same computation. So even if you know the computation, there are many different ways of doing this. So one would be interested in finding out what the algorithms are or the representations that are used to achieve these computations. And of course, these things have to be implemented. Right now, I did the calculation. You can use a calculator, you can use paper, you can use anything you want. But there are many ways to implement the same algorithm. So you have 3 things: computation, algorithm, and implementation. So one can understand the mind or specific cognitive processes at these 3 different levels, and different people focus on different levels. And of course, people also try to relate how one level or something happening at one level is linked to something happening at the other levels. I'm just going to take only one example and focus on the middle level. And that essentially relies on representations. So we create visual representations. We do mathematics, there are representations. We talk, there is language, and we have linguistic representations. And these representations have some structure. In this case, I have just put an example from language, and what you have is a hierarchical structure, right? This is just parsing. You can parse the sentence. Now, this particular sentence can be parsed as, this is an example of syntactic disambiguation in terms of two ways, and both ways are shown here. And essentially, we shall discuss violence on TV as two meanings, right? And these two meanings are essentially shown by two different structures. So one can say that, well, depending on the structure of representation you have for the sentence, that you can say in your mind, you will actually obtain a different meaning. So here, semantics meaning depends on the way you have parsed this particular sentence. So the key here is the nature of representations matter. How they are structured is going to matter for how people understand what, say, for example, a teacher teaches in class. Now, there are pretty much all cognitive processes are important. This is just a kind of a subset or a small list. Attention, Kavita mentioned it, is very important. I study attention fairly a lot. Memory is very important. Pretty much everybody knows that. How we solve problems is important. Metacognition is important. And even more recently, people realize social cognition and how we handle our emotions are very important for learning, both in life as well as in a classroom. In fact, there is a recent volume published by last year by UNESCO about social emotional learning and its importance for education. So I would like those of you who are interested in this is to check out this volume published by the Mahatma Gandhi Institute in Delhi. What I'm going to do, given the amount of time I have, is going to focus a little bit, not necessarily cover everything fully, on attention, memory, and problem solving. So the main thing about attention, as those of you know, is the idea of selection, that we select. We select information that is available to us, and this is basically something that we do based on its importance or salience. And we select based on many aspects. So in the context of visual perception, which is something I study, we select based on location, where something important is happening, or objects, what objects are important, and so on. So selection has some basis. The basis is, it can be anything. There are various aspects on which or based on which we select. And the selection can be based on information that is available in the environment. Sometimes we call them stimulus control, or goal driven. You can actually control it based on the kind of goals you have. And these differences matter. The reason is that the processes that are involved in attention, the mechanisms, depend on the way in which selection happens, the mechanisms, the factors that control selection, and so on. Once you select something, there are consequences of selection. So what are the basic consequences? Well, the first obvious consequence is that you perceive. So in a strong version of this hypothesis, you will say whatever select is what you perceive. You can cognize, you can think about what you have selected. And of course, you can also perform various actions based on whatever you have selected. So selection can be for perception. Selection can be for conscious awareness. Selection can be useful for, important for storing information in memory, your decisions making, and of course, important for the actions that you do. So selective attention is a very key cognitive process that influences pretty much all the other cognitive processes that happen. I'm just going to give you 2-3 quick examples. One of the theories of selective attention, which is important, and there are many, is something called the load theory. So what does load theory say? Load theory says that if you have goal-directed behavior and you want people to focus your attention on something relevant for your goal-directed behavior, the load theory proposes that there are two mechanisms that are available that we use. The first one is a perceptual selection mechanism. So it is passive. Essentially, whenever you select something, there are distractors. These distractors are something that you do not want to select. You have a fairly difficult task to do. These distractors are there, and you essentially exclude them. You filter them out. And this is a fairly passive process, and it happens when your perceptual load, the amount of resources that you need to do a task, is high. What happens when you have an easy task? When you have an easy task, interestingly, what happens is that the distracting information actually has a much more influence. You can't filter them out easily because the task is easy, so the distractors also, in some sense, get into the system. They load up your working memory, and that actually reduces your performance. So one interesting implication of load theory is that you actually have much more distractor interference when you are doing an easy task compared to when you are doing a difficult task. The second thing I want to ask you to pay attention to is the fact that your attention can also change in terms of its scope. And this is something that I study, so it's dear to me. So you can, to use a metaphor, you can think of it as a zoom lens. So you can zoom in and focus on something, or you can zoom out and then kind of look at the big picture or the larger picture. So the zooming in, zooming out has implications for how you process information and how that affects subsequent cognitive and emotional processes. So the other thing in terms of what is selected is the scope of selection, whether you can zoom in or zoom out. The third thing, as I said, just to show you an example of how important attention is. So I'm going to ask only Kavita. Actually, we do these things in class. I'm sure she has seen it before, but still, I'm going to show you some scene which is going to flicker. There will be a scene, and there will be a scene in which there will be a change in the original scene and back and forth. And I would like Kavita to find out what the change is. Have you found out? Or anybody else who have found out can tell me quickly.
No,
Okay, so
wait, sir, wait. You can't. I'll fail if you do this. 1 second.
So the engine of the plane is missing in one of the pictures.
Okay, so sorry, Kavita. I think Anjali found it first. If you look at the center here, the engine, which is actually right in the center of the scene, and I'm sure many of you have not detected this change, even though this change is a fairly big change. So one of the interesting issues is that while the scene or what we see look like we are taking in a lot of information, unless we are able to pay attention, in this case, the flicker disrupts attention, you don't perceive. And of course, if you don't perceive, you cannot store and you cannot do much with it. So this shows, I mean, there are many other demonstrations in the internet, how important attention is for perception. The second thing is that, of course, information is available in different dimensions, and sometimes they conflict with each other, sometimes they go with each other. And one simple, psychologist experiment that we do is essentially what is called a Stroop task. And basically what you see here is a bunch of color words written in different colors. And then if I ask you to read them, say the words in the first box and the words in the second box, and all of you can see in the first box, red color is written, red word, the word red is written in red color, the word green is written in green color, and so on. Here, there is a conflict. The word green is written in yellow, the word red is written in green, and so on. And what you find is that people take much more time to, let us say, if I ask you to report the color of the words, people take much more time here with this bottom box words than the top box words. Now, this is a simple laboratory measure of how much we are able to control information that are irrelevant. Interesting thing is that, which I do not have, this cognitive control, the ability to control irrelevant information so that it doesn't affect your performance, actually changes with age. So children show, if I take the difference between, say, response time for words in the bottom box minus response time for the words in the top box, this difference, which we can call a Stroop effect or a congruency effect, this effect is much larger for very young children. And as children develop and grow into adults, this value actually decreases with age. It is not a linear decrease, but still the fact of the matter is it does decrease with age. And interestingly, studies have shown the magnitude of this effect can be related to, or we actually did a preliminary study where we found that it is linked to academic performance. So your cognitive processes, it is not simply what you teach or not. The way cognitive processes develop influences your academic performance. And of course, you can practice. You can even improve this with practice. So we have done a study where we have compared students who practice meditation in one school and students who do not practice meditation in another school. And we showed that students who practice meditation actually have lesser interference. They show a smaller effect than others, and so on. So people have shown this. So cognitive control, in a way that we can measure using simple experiments, can actually predict your academic performance or influence your academic performance. Of course, the next thing is that we do things in time. So we do some task, then we ask the kids to do another task, and then we ask the kids to do another task, and we actually keep on changing these things, tasks to do. Even in terms of schooling, we have one period we teach math, another period we teach physics, another period we teach English, happens every 40 minutes, 15 minutes, depending on the school. Now, one interesting thing I have always been wondering is that why that is the case. There is really no research that shows that having these periods for 40 minutes, 50 minutes, and keep on changing the subject that gets taught is really good for anything. But this has been going on for, I don't know, 100 years or so, I guess. And at least in the lab, when people switch between one task to another task, there is a cost involved. We call it switching costs or mixing costs. Essentially, you switch from task A to task B, there is a cost in terms of your slowdown or you make more errors and so on. And this is something that can be measured, and we have actually measured it in children over multiple age groups. And again, we find differences in switching costs as a function of age. We have used tasks which are shown on the screen. Essentially, the children are asked what number and how many. They remember the stimuli are the same. It is just what you do. The task is different. In addition, when we do make mistakes, our children make mistakes. If they make a mistake, then they slow down. And this slowing down, which is sometimes we call it post-error slowing, also changes with age. And it is a process of normal cognitive development that switching costs, post-error slowing, cognitive control, selection of selective attention in whatever way we measure, we can see that they change with age from 3 years old to 17, 18 years old into adulthood. And this is very critical or important to understand that these cognitive processes themselves are developing, and it is not that it is the same in a 5-year-old child versus a 10-year-old child. Their cognition itself is different, and if we don't consider that when we teach, then we are going to make mistakes, right? The next thing I want to talk about is memory. Now, memory also doesn't come in one single module or domain. We have, based on the time scales, we have 3 types of memory: sensory memory, short-term memory, long-term memory. Sometimes we call the short-term memory working memory. And long-term memory also has been fractionated, divided into many other types. Declarative memory, which we can verbalize in language; procedural memory, motor skills that we cannot verbalize; and declarative memory also you can think of in terms of episodic memory and semantic memory. So there are different types of memory, and there are different types of mechanisms that are involved. I'm going to focus on only a couple of issues in memory, and hopefully that will be of interest to you. The first thing we do important for memory is we chunk. And I'm sure many of you know we chunk information. When you are given a long list of numbers, we chunk them. Similarly, as you can see in the example here, you have a string of letters. If you try to remember them without chunking, it's much harder. But as you have seen in the second line here, that if you underline them in terms of a chunk with 3 letters, it actually has some meaning. This is an American example. You can fill it with Indian examples: CIA, FBI, NBC, CBS. Now, this is much easier to remember, even though the total number of letters to be remembered is still 12. So, an important aspect of remembering is chunking. And if information is chunked efficiently based on various association and the knowledge that you already have, then it is easier to store and remember them and recall them and use them much more easily. There are many different factors that influence how we encode information, and we are able to remember better. This is a list of them taken from a basic book on memory. Well, the one important thing is to create connections. So, for example, if you have a word and you are teaching a word to your child, if you use it, you ask the child to link it to something that they can imagine, right? And then they are able to encode and remember information better. Link to self. If you somehow make it relevant to the self, the person who is learning, then people remember better. Active creation. You ask people to generate information rather than giving all the information. You ask people to generate so you give partial information and then make them generate information. That also leads to better memory. Testing, which I will talk about later as well, actually improves your memory. The way information is organized also makes a huge difference. So people have shown experiments where if you present information in a certain organized way in terms of a structure, like for example, a tree structure, then people tend to remember information much better than something that is presented in a less organized manner. Or do you present it in a very meaningful framework? And so on. Now, this is as far as encoding is concerned. What about retrieval? Well, the first thing to note is that what is called the encoding specificity principle. That is, normally to learn, even though there is some material, there is always a cue, or a more general word is context. These cues that we use when we learn information become effective later when we are trying to retrieve information. So essentially, if the same cues are given, then people are able to retrieve information much better. People have done many different studies to show this. So the if, for example, you learn something, then some information when you are in a bad mood, hopefully not, then actually if you are able to retrieve it better when you are in a bad mood. The same thing applies, of course, to happy mood. People have shown, if you remember, if you store or encode information in, say, underwater, then you are able to retrieve better underwater. So even the place in which you learn matters. So to put it another way, you teach a kid in one classroom, you give the test in the same classroom, the kid will probably do better than putting the kid in a completely different classroom, which is what we actually do in our board exams. So, what influences memory? This is from a very early model of memory. All the details are not important. But the only thing I want you to look at is when you code information, it is not that, let's say you're studying a word, which is shown here. The study context is also encoded along with the word itself. So the context in which you have heard the word is also stored along with the word. Now, when you're asking people to recall, you have a test context. And this test context, if it is closely related to the study context, then the chances of retrieval for the study word is much higher. And this is a fairly simple principle. This shows one important fact, or the way in which, say, a computer memory is different from human memory. Human memory is always context dependent, whereas computer memory is not context dependent. So one thing we have to remember is that all information is stored in terms of a particular context. And knowing this helps in both, I'm sure, for learning ourselves as well as for teaching. Let's look at another example. Now, this is a more of a slightly abstract reasoning task. If you are not familiar with this task, this comes from Wazen, so it's called a Wazen selection task. The task itself is shown at the top. And the way this goes is like this. You have 4 cards on which one side you see E, K, 4, and 7. On the other side, something is written, which of course you can't see. So there is a rule that describes it. It says if there is a vowel on one side, then there is an even number on the other side. Now the question is, what is the minimal number of cards you need to flip to see this rule is right or wrong? So if you want to verify this rule, if vowel then even number, what are the minimum number of cards that one has to flip? Anybody quick answer? Tell me the cards. Anjali, since you answered before.
So is it just one?
Which one?
Just one card. If you just flip one card, you know.
Yeah. Which of the 4 cards? Tell me the card also. E, K, 4, 7. Which one?
E.
E. Okay. Right. Now, this is, I'm not going to do this actual demonstration more, but the actual answer is 2, not 1. And the correct answers are E and anybody else? What's the second one?
4.
4, the answer is wrong, actually. It's 7.
7.
Right. So why? Well, this is essentially sometimes people use it to talk in terms of confirmation bias. So actually, it is 7 that can disconfirm this rule or hypothesis. So if, for example, you flip 7 and there is a vowel, then this rule is wrong. Now, this is also related to what other people talk about in decision making. Now, this is not what is important here, and that's not the purpose I have put it. What is important is the one at the bottom. So people have done this experiment rather than using abstract symbols like EK47 and a rule, if vowel then even number, you change it to something more meaningful. Okay? If drinking beer, this is US example, then over 19 years old. You can also make it marriage or something else, where there is a deontic rule, there is a legal rule. Now, when you change this, the structure of the problem is still the same, You have beer, soda, 16 years old and 24 years old, right? You can see it's pretty much the same structure. Now, the interesting thing is, I want you to focus on the results on this panel. The red shows when the problem is given in an abstract form, very few people do it, and this is actually adult data, not children data. But when you convert it into a meaningful semantics with beer, soda, or age and all that, actually many more people get the answer and do it correctly. So this shows, even though structurally the rule to be learned here or verified here is the same, the way in which it is presented matters. The next thing I want to talk about is problem solving. And of course, if you are a teacher, you give lots of problems. We as students have done many problems. Some problems, of course, are solvable, like maths problem. There is a correct answer. But as you go to the university, people ask you to write term paper. Sometimes people ask you what is the best movie you have seen. You have to find roommates, maybe find people to marry, decide whether to do PhD or not, find a solution to your chess problem. All of these are problems. Some are well-defined problems with correct answers. Some are ill-defined problems where the answer is not clear-cut at all. Now, Gestalt psychologists, interestingly, started talking about it. And one of the things they focused on, and which is linked to the earlier word that I mentioned, representation. And the Gestalt approach says that how you represent a problem. Now, problem is given, you write it on the whiteboard, but once it's written on the whiteboard, as a learner, I make a representation of the problem in my mind. Now, if the representation of the problem I have in my mind is not the representation, let us say the teacher intended, or it is needed to solve the problem, then actually I will find it very difficult to solve the problem. It is not because I do not know the steps of how to solve the problem. I actually misrepresent the problem itself. And this is something a lot of people, sometimes people don't realize. So changing the way the problem is represented can have an impact on how the problem is solved. I'm going to take two examples, but I will start with one example. And essentially, the way a problem is represented, that representation is what is going to be used to retrieve relevant information from long-term memory that actually you want to use to solve the problem. Of course, if the problem is misrepresented, you have a block. You do not know how to proceed. So the only way you can proceed is somehow you need to change the way you have represented the problem. This can occur through elaboration, that is, you provide more information, or constraint relaxation, that is, you reinterpret the rules, or re-encoding. Sometimes you remove what we call functional fixators. And of course, you get an insight when this block is broken and you feel like, now I know how to do this. So what is really involved is the way or critical aspect here is the way you represent the problem. Right. So let's look at an example here. And this is a problem from Kaplan and Simon, which is called the mutilated checkerboard problem. And the problem is this. You have a checkerboard.
Sir?
Yeah.
Sorry, there was just one question.
Sure.
From Durga Bhavani. She said, can you give an example? I think it was for the previous.
This one? I'm going to do it. Okay. So just hold on, and if this is not clear, then you will see. So here is an example I'm actually giving. This is a checkerboard. It has 64 squares. You know, checkerboard, they have alternate colors, right? White, black, or in this case, blue, gray, and all. If you have a domino, which also has two parts, and you place dominoes, and with a single domino, you can cover two squares. You can place them one next to each other. The question is, you can cover the 64 squares with 32 dominoes. Okay, it's trivial. Now, if you eliminate the two opposing corners, so let's say you eliminate this corner and this corner, Now the question is, can we cover the remaining squares with 31 dominoes? And if yes, how? Anybody? So the person who asked the question about represent example should answer, ideally, if possible. Okay. Anyway, let's hold on. Yeah.
It can't be done.
Can't be done. But let's see how it can be done. So they did the same experiment with 4 different conditions, right? You can have blank squares. You can have 2 colored squares, like the one I showed. You can actually put them in verbal form, black, pink, okay? Black, pink. Or you can write different words. In this case, bread, butter. All of you know bread and butter go together, right? Okay, so when you remove the 2 corners, what goes? This and this. What do you lose? The person who answered, Harun?
2 of the same.
2 of the same goes. So actually you lose the 2 butters. Obviously, that means you cannot have a bread butter combination, 31 of them, right? Because you have lost 2 butters actually. Now this is so obvious once you put it like this. So they did the experiment and showed that people performed better this way rather than even this version of the problem. You give them butter bread, and essentially, because now you know bread and butter go together. And that extra bit, the way you represent information, is changed, right? And this change in representation enables you to make this problem much more easily solvable. Because structurally, from a math perspective, the problem is exactly the same. It doesn't change. But the way you represent changes, and once you change that, the problem becomes solvable. And you can do this with analogies as well, right? All of us like analogies. And here is another analogy, which is another version of the bread and butter. In a small village, there were 32 bachelors and 32 unmarried men. The matchmaker succeeded in arranging 32 satisfactory marriages. Then one drunken night, 2 bachelors in a test of strength killed each other. Can the matchmaker come up with 31 heterosexual marriages among the 62 survivors? Now, immediately all of you can see this problem is actually exactly the same problem as before, is much more easily solvable, right? It's a bit variation of the bread and butter example. So once you give an analogy, now people can make an analogy. Okay, male, female, in this case, a white square, black square in that case, and the 2 corners are similar. In this case, the 2 corners are the bachelors, and wow, so which means it's not possible. It's a very simple problem, obviously, but it is still useful to make this point that the way you represent the problem is important. And if you can't solve it, then you need to change the way the learner has represented the problem. So if the learner is having, say, struggles to solve a problem, then the first thing as a teacher you need to find out is how exactly has the learner represented the problem? Not that whether they know the answers of the steps. How the problem itself has been represented in their mind. At least in my example, at least when I was a student, a lot of people don't pay much attention to it. So you have another analogical story. You have to look at this relationship, make a correspondence, a mapping, then you can come up with a parallel solution. Let's look at another example, which is an interesting example. Some of you may have seen it, then you will know the answer. If you do not know the answer, you can try it. What I'm going to show is, present a simple problem. You have 9 points, 3 each in a row, 3 dots in a row. You have 9 dots. Your problem is you are supposed to draw 4 straight lines to join all the dots without taking the pen off the page. Unfortunately, we are doing this online, but you have to imagine it, or if you have a pen and paper, you can try it. Start tracing, but you are not supposed to take the pen off the page, but connect all the dots using 4 straight lines. Okay? I just give a few seconds for you to think about. We are running out of time, so we will not actually allow you to solve the problem. So I will give you the answer and apologize for giving the answer. Okay? Anybody has figured it out by now? Okay, so the answer is, interestingly, this problem was given at Disney. Right. So what can somebody tell me if this is the solution? What is the difference between the way you may have tried to solve and here?
When you say connecting the dots, normally the brain thinks that, only the connecting, it's not, it's just go a little bit away from that. No, that is what the thinking.
Yeah. So here the representation is that you did an extra bit here, and the extra bit is to think that your line is supposed to end with the dots, which of course is not specified in the problem, but this is the extra bit which becomes part of the way you represent the problem, and that is the reason you have difficulty solving the problem. The moment you take that out and say that, well, the line can go past the dots, then the problem is not that difficult to solve at all. Okay? Now, so the last section is, I have some examples from research on education. As I said, these are some old examples I used to know, so I'm presenting them. You may want to find out more information or more recent work done by others. The first thing I want to do is to present a list of choices. This comes from a paper by Nathan and Codinger. What you see is a problem type. There are 6 problems. The only difference here is how the problem is presented, right? You have, for example, things like starting with 81.9, if I subtract 66 and then divide by 6, I get a number. What is it? Now, immediately all of you who are know a little bit of math, school math, know that all the 6 problems are the types are exactly the same problem, and the answers are also the same. It is just the way the problem is presented. Now, in their study, what they did was they gave these 6 problems to teachers, and then they asked the teachers, rate them in terms of order of difficulty. Okay, so whatever is the least difficult, what they think or they thought for the students, what would be the least difficult and what would be the most difficult. This is the difficulty level of the problems from the perspective of the teachers. And this is the rank, right? The teachers went from 1 for this, 2 for this, and 6 for this. Okay, fine. Now, these problems are actually given to students, and then they got this performance from the students. And this is what you get. What do you notice? They don't match. So what the teacher thought was difficulty levels of these problems from 1 to 6 is not actually, doesn't match with the actual student performance. So and in fact, the rank correlation is 0.09, which is not much at all. So this shows that what the teachers think what is difficult for the child may not be what the child finds difficult. And this is a mismatch, and this mismatch is important to understand and hopefully remove, right? And that is the reason why you need more cognitive research and research in schools.
Mr. Narayanan.
Yes.
Even if you look at that, the student performance when they gave the order, reasonably they say the difficult ones is the problem which has the language part.
No, actually this goes from easy to difficult.
No, when the student said the first one is the difficult, the choice is the 1 is the easy one.
Yeah, 1 is the easy one, 6 is the difficult.
Okay. Because most of them, the language part is the translate of the problem into, when the language part is given, into equations. I thought that is how okay, right.
Yeah, anyway, so no, even otherwise, if it is different, my main point here is that what the teacher thinks difficult and what the actual student performance, based on that, we get the difficulty. These two things do not match. Different kinds of setups, these actual numbers may change. And
I
this
think this will never match also, I think. Even in future also, it will never match.
well, I hope not, but let us see. Let's
Because
not
each one is the unique, no? The way they think is really is unique. So different perceptions about the problem. So
okay. Now, the second point I want to make is testing. Now, this is an important point, is the way in schools, including up to board exams, the way testing is used. Testing is used as a way of measuring performance, who is doing well, who is not doing badly. But from a cognition perspective, testing is actually, that's not the purpose. I mean, you can use it, but really the case that it can actually aid your learning. Now here testing as, think of it as an intermediate step rather than a final step that happens at the end of the semester or end of the year or end of school education. But in terms of a way that you actually learn. So here is a study that by Rodiger and Karthik, done in 2006. So they asked their subjects to read a passage for 7 minutes. Then they asked people to do math problems for 2 minutes. Then they had 2 groups. In the testing groups, people were given a test for a recall test for 7 minutes. In the other condition, we say they just reread the passage. So normally even students do that. They read once, then they read again, then they read the third time, before exam also they read, and so on. So they just reread the passage. Then there was a delay. There were 3 delays, 5 minutes, 2 days in 1 week. Then they gave a recall test. This is a testing. The test is the same in both cases. It's just recall whatever they have learned. So what's the finding here? Now remember, the one is a testing group, the other is a rereading group. When the gap, the delay is 5 minutes, really there wasn't much difference, and obviously if only 5 minutes have passed, people did fine. The rereading was even looks like slightly better than testing. But see what happens with 2 days and 1 week. People who having read once, if they had actually written a test, they actually remembered better than those who actually reread the material. So what this shows is that testing as a method of learning, that you give a test, it actually makes you better, rather than simply reading the material again and again. Another study makes the same point. This is a simulated classroom setting. Participants viewed a series of 3 lectures on consecutive days. They studied a lecture summary. They took a multiple choice test. They took a short answer test. Feedback was given for all the questions and so on. Then there was a final comprehensive short answer test after 1 month. Again, the basic idea is that those who took the test essentially performed much better after 1 month than those who did simply reread it. So this shows that how testing in the classroom itself can be used as a tool so that they learn the material better, rather than, I mean, we are not worried about the final exam or board exams. So just to kind of summarize about memory, this is from Willingham. There are 3 points that he makes for as far as from the perspective of education. Memories are formed as a residue of thought, right? If you want to remember, then you need to select a mental task that will essentially involve going through its meaning. And we said that when we talked about what makes your encoding better. If you want to remember that has little meaning, then you can use a mnemonic. But otherwise, meaning is important because our memory is context dependent. Memories are lost because of missing cues or ambiguous cues. So one way you can take care of it is to make memories distinctive. And to do that, you actually need to distribute your studying over time. And you have to, as I said, give tests and all. The third thing is individuals' own assessments of their own knowledge is fallible. In fact, most people if you ask them how much they know or how they performed in an exam and so on, actually tend to, they're not able to estimate it very well. So the best way you can do it is to test yourself. And if the test is similar to what you're going to take eventually, then it's a similar type of test. So some quick suggestions for teachers: you present knowledge in a form that facilitates effective encoding, and students can incorporate into a coherent knowledge structure. You provide opportunities to actively use information, and you do frequent reviews and testing. This is something that I just put because sometimes teachers tell me that students have different learning styles, like visual learning style, verbal learning style, and if our teaching matches with those learning style, then learning is good. So sometimes called the machine hypothesis, where instruction is tailored to suit, say, visual style or auditory style or whatever. Unfortunately, there is very little credible evidence for it. There is an interesting paper by Pashler and colleagues in 2008 to show that there is really no credible evidence that people differ in terms of, people of course may have, or they say they prefer something, but the fact that if you match the learning with the so-called learning style, the instruction matches, somehow your learning will be better. I took this from a report published by the National Institute of Education Research or something in the US. And what you see in this table are a bunch of recommendations and the level of evidence that is available in terms of scientific evidence for these things. Just to see one of them, spaced learning over time. You have moderate level of evidence. Interleave worked example solutions, problem solving exercises. You have moderate level of evidence, and so on. When we go, let's say use quizzes to promote learning. Now that's good, but if you use pre-questions to introduce a topic, actually a lot of teachers do that. Actually, apparently the evidence is very low for it. You use quizzes to re-expose students to key content. So use quiz as a method to re-expose key top content to students. It actually has strong evidence that the kids learn better. Similarly, asking deep explanatory questions has strong evidence. So by looking at evidence that comes from cognitive science or cognitive psychological studies, which involve studies in the classroom or studies done in the lab, you can actually find out what has fairly strong evidence and then try to incorporate that, right? So let me skip it. I think I probably run out of time. You can read this on your own, I guess. So to conclude, cognitive science provides, and this is a quote, an empirically based technology for determining people's existing knowledge, for specifying the form of likely future knowledge states, and for choosing the type of problems that lead from present to future knowledge. So if our educational practice is grounded in cognitive theory, and Resnick says it would transform the whole curriculum in fundamental ways, it would treat the development of higher order skills as the paramount goal of all schooling. And all I want to add is to say that it is important that the cognitive processes of children develop and we aid in its development, because if the cognitive process develop well, naturally learning will be better. Thank you.
Thank you, sir. That's wonderful. I failed 2 tests, so I'm not even supposed to be talking now. But sure, like all bad students, I shall do so. Sure. I shall talk. But thanks a lot. We are running out of time, but there was one interesting point. I mean, we still go with this 40-minute class or 1.5 hour class as it goes. And that means that's a longer time that you're sitting through one full subject rather than actually jumping from class to class, as against attention, which says that you have very short attentional spans. I mean, 8 minutes, 10 minutes has been this one. What is your optimal, what needs to change? Do we keep a whole day for math only, and then is that better, or is it?
Well, it's a good question, but I don't think rigorous studies have been done yet. for the thing about timetables and which we do for school periods and all that actually was developed simply to optimize where you can go make one teacher go to another section, another teacher go to another section to manage the logistics of assigning teachers of different subjects and go and teach in different sections or classes and so on. So it was really developed for that purpose, not for any, in fact, I don't think there is any published study even for the origin of this, which probably started, my guess is somewhere in early 20th century.
Yeah.
Coming back to it, it's a good question. I think this is something that we should study rigorously, which has not been studied because no school wants to change these things. Everybody follows every other school, and then we are stuck in this method, so to speak, including engineering colleges, higher education institutions, and so on and so forth. So
I wish to add that the school system is designed to be quote unquote resource efficient.
Sure.
It is not necessarily child centric.
I agree. I have no disagreements. But as a scientist, all I would say is this is a wonderful question, but I think we should actually study this. If you see infants, they actually do the same thing again and again. Of course, when they get bored, they do something else, but then they will come back, depending on their attention span. But they determine their attention span. So when they are not able to sustain their attention, they do something else. But then if they find it interesting, they will come back to the same thing. So we probably need to have breaks. It is definitely true that we can't sustain our attention over long periods of time. But after the break, maybe sometimes we should come back to the same thing. What happens in schools is, at least if you think traditionally, the bell rings, then everything changes. Even a teacher in the middle of a sentence stops and then goes and does something else. So
I think we can't take any questions, but I just wanted to add that there was one study. I mean, it is not a study, but it was a case study report somewhere online in Turkey. They have the system where the child comes in and there are classrooms. Each one has a math, science, English written. The teacher is sitting inside. The child comes and decides which class they want to enter. So that child spends for almost 4 hours in that class, and then, but they have a strict rule of saying that per week you need to spend so many classes. So maybe that's something that we can try.
Yeah, there was a comment in the chat box as well about other types of schooling. So it is there, but what is missing are probably very rigorous studies of measuring its both short-term impact and long-term impact.
Yes,
that's what we really need at this stage.
Thanks a lot, sir. Thanks a lot for coming in and giving
Thanks
this
a lot
talk.
for calling.
Thanks a lot. Our director, Professor Pijayan, is there, so he also can convey his thanks.
Sure.
Pijayan.
Yeah. Thank you. Thank you. And I don't want to take any more time. Thanks for.
Thanks a lot. Yeah.
Thank you, sir.
Thanks for the invite.
Ma'am, can you please wait? I want to.
Yeah.
This
Yeah.
session.
You have not live anymore, Srikanth?
One
No, he's just turning it off.